Welcome to the deep dive. Okay, get ready because today we're plunging into, well, one of the most fundamental questions in astronomy.
Uh-huh.
How do stars get their mass?
Hmm.
We're talking about something called the initial mass function, or IMF for short.
Yeah, the IMF. And why does it matter? Well, this distribution, it's like the bedrock for understanding how stars form in the first place.
Right, for the very first stars way back when,
Yeah.
to how whole galaxies actually evolve over time. It's huge.
It really is central. You can think of the IMF as maybe like the birth weight statistics for a whole bunch of stars born together.
A birth weight chart. I like that. It's an empirical snapshot, right? Describing the distribution of what those stars initially weighed.
Exactly. And we've got some great sources that trace the history of this idea, the big debates astronomers have had.
Oh yeah, decades of debate.
For sure. And also the tricky business of actually measuring it and critically how brand new super precise data is changing things.
Especially from the Gaia mission, right? That seems to be popping up everywhere.
Gaia's been revolutionary. It's giving us this amazing view, particularly in our own galactic neighborhood.
So our mission here in this deep dive is to really unpack what the IMF is, why there's been so much argument about it.
Its properties, whether it's the same everywhere.
The challenges in observing it, and yeah, what Gaia's recent data, this high accuracy stuff, is telling us about how it looks right here locally.
So by the end, you should have a really solid grip on this core concept and hopefully see how these new observations are, refining our picture of the cosmos.
All right, let's dive in. So the IMF, at its heart, it's an empirical description, like you said. It's what you measure.
Right. You look at a young group of stars just formed, and you basically count how many have a certain initial mass.
And historically, how did we first characterize this?
Well, the foundational work was really back in 1955 by Edwin Salpeter. He looked at stars in our solar neighborhood, focusing on the more massive ones.
The big guys.
Yeah, bigger than about one solar mass. And he found this clear relationship. The number of stars dropped off pretty steeply as the mass went up.
More massive stars are much rarer. Makes sense.
Exactly. He described it with a power law, a mathematical formula, with a slope around minus 2.35.
Okay, so a simple power law for the heavyweights. But stars come in all sizes, down to tiny little red dwarfs. Did that single law work for them too?
Not quite. Later work showed that for those lower mass stars, the distribution doesn't keep falling so steeply, it kind of flattens out.
Okay, so the simple picture needed adjusting.
Right. Which led people to propose different mathematical ways to describe the whole mass range better. You could still use power laws, but maybe break them into segments.
Like a broken power law.
Yeah, exactly. Krupa suggested that in 2001, different slopes for different mass ranges, or another idea from Chabrier in 2003 was to use something called a log normal form.
Log normal, how does that work?
It sort of rises to a peak at a certain mass, typically around a fraction of a solar mass, and then falls off towards both the higher masses and the lower masses.
Okay, so different shapes to try and match what we actually count across the board.
Precisely. They're all just ways to better capture the observations, the actual counts of stars at different initial masses.
So that's the description side, how it looks. But then there's the physics, the theory side.
Right.
Why does it look like that?
Right. How do star-forming clouds produce these specific distributions? Why do stars end up with the mass they have? That's where theories of star formation come in.
Trying to predict the IMF from, like, first principles?
Yeah, from the physics of collapsing gas clouds. One big idea involves fragmentation and something called competitive accretion.
Fragmentation and competition. Sounds dramatic.
Well, imagine a giant gas cloud collapsing. It doesn't just shrink smoothly, right? It breaks up, it fragments into smaller clumps.
Okay.
And then these clumps, these protostellar cores, they start pulling in gas from their surroundings, and they can kind of compete for that available gas.
So they're like little gravitational vacuum cleaners fighting over dust bunnies.
Sort of, yeah. And models based on this idea from people like Larson, Bonnell, Hennebel, Chabrier, they suggest the final masses depend a lot on the cloud starting conditions.
Like its chemical makeup, how well the gas cools, things like that.
Exactly. The turbulence, the cooling efficiency, how the clumps interact, it all plays a role in setting those final masses in this picture.
Is that the only theoretical game in town?
Oh, no, not at all. There's another important perspective that focuses more on self-regulation.
Self-regulation. How does a star regulate itself?
As a protostar forms and pulls in gas, it heats up. And it starts to radiate energy, right? Light, heat.
Yeah, fusion eventually kicks in. But even before that, just the compression.
Right, even the accretion process itself generates heat and radiation. And this outward radiation pressure can actually push back against the gas that's trying to fall in.
Ah, so it's like the star starts fighting back against being fed more.
Kind of, it's a feedback loop. Theories like those by Adams and Laughlin suggest that stars sort of settle on their final mass when this radiation feedback balances the inward pull of gravity and accretion.
Okay, so in that picture, what determines the final mass?
It would depend more on things like the density of the gas around the star, how much angular momentum it has, how fast it's spinning, and importantly, its metallicity.
Metallicity, the amount of heavier elements. Why does that matter for feedback?
Because metals affect how opaque the gas is, how easily radiation can push on it. More metals can mean stronger feedback, potentially limiting the mass more effectively.
Wow, okay. So two quite different theoretical angles of fragmentation and competition versus feedback and self-regulation. I can definitely see why figuring this out observationally would be, well, challenging.
Absolutely. And that complexity, combined with the difficulty of observation, led to this long-standing, pretty intense debate.
The big one is the IMF universal.
Exactly. Is that distribution of initial masses the same everywhere, every when? Or does it change depending on the environment?
So the question is, if you look at stars forming today in, say, the Orion Nebula versus stars in an ancient globular cluster, or even stars in a distant galaxy.
Do you get the same relative number of heavy stars, medium stars, and light stars? That's the core question.
And the evidence was conflicting for a long time.
Oh, very much so. Some studies seem to show remarkable consistency pointing towards universality, which honestly would make life much simpler for astronomers.
Yeah, you could just assume one IMF fits all.
But other studies kept finding hints, or sometimes strong evidence, of variations. Some places looked bottom-heavy.
Meaning more low-mass stars than expected.
Right. And other places looked potentially top-heavy.
More high-mass stars.
Relatively speaking, yes. So the picture was messy.
Before Gaia really started weighing in with precise data, what was the general feeling? Was there a consensus leaning one way or the other?
Around, say, 2010, reviews often summarize the consensus as, well, that the IMF seemed relatively invariant. Most people thought it was probably pretty similar across most environments after the very first stars.
The first generation population 3 stars, they might have been different.
Yeah, the conditions in the very early universe were so different, basically no metals, that most theories predict those first stars might have been much more massive on average, a very top-heavy IMF. But after that, the thinking was maybe it settled down.
But there wasn't really knockout evidence either way.
Exactly. The observations just weren't precise enough or didn't cover enough different types of environments with enough certainty to definitively say, yes, it's universal, or no, here's exactly how it varies. There was wiggle room.
Which brings us right up against the practical problem. How on earth do you actually measure the initial mass function? You can't exactly watch stars being born and weigh them.
No, unfortunately not. You have to work backwards from what you can see.
Yep.
And what you measure directly is the present-day mass function.
Okay, the distribution of stellar masses in a population now.
Right. But, and this is absolutely crucial, the present-day mass function is not the initial mass function.
Because time messes with it.
Exactly. Two big things change that original distribution over cosmic time. First, stellar evolution.
The massive stars burning out quickly, we mentioned that.
Right. High-mass stars live fast, die young. They burn through their nuclear fuel way faster than low-mass stars like our sun or red dwarfs.
So if you look at any reasonably old group of stars, like billions of years old,
all the stars that were initially born with high masses, say above 8 or 10 times the mass of the sun, they're long gone. They've exploded as supernovae or collapsed into neutron stars or black holes.
so the high mass end of the distribution just gets chopped off over time.
It gets depleted, yeah. And then there's the second process, dynamical evolution.
Dynamics, meaning stars interacting with each other gravitationally.
Precisely. Especially in crowded places like star clusters. Stars are constantly tugging on each other. Over millions or billions of years, these interactions can actually kick stars right out of the cluster.
Like cosmic billiards.
A bit like that, yeah. Close encounters can accelerate stars, sometimes enough to reach escape velocity.
And who gets kicked out more easily? The lightweights.
Often, yes. Lower mass stars are generally less tightly bound gravitationally and easier to accelerate during an encounter. So, over long timescales, dynamical evolution can preferentially deplete the low-mass end of the population in dense environments.
Okay, wow. So stellar evolution eats away at the top end, and dynamics can eat away at the bottom end. to get the initial function, you have to somehow correct for both of these effects.
You absolutely do. You need to model how stellar evolution has removed massive stars and how dynamics might have ejected low-mass stars based on the age and environment of the population you're studying. It's complex.
And that's before we even talk about how hard it is to know a star's mass in the first place.
Oh, yeah. That's the other huge challenge. The absolute gold standard, the most direct way, is using Kepler's third law for binary stars.
If you can see two stars orbiting each other.
And track their orbits precisely, yeah. The orbital period and separation tell you the total mass, and how they move around their common center tells you the individual masses.
But you can only do that for a handful of nearby systems where you can resolve the two stars and watch them long enough.
Exactly. Maybe 100 or so systems give us really precise, direct mass measurements this way. It's fundamental, but it doesn't give you the statistics for thousands or millions of stars.
So, for the vast majority of stars, how do astronomers estimate their mass? It's not direct measurement.
No, it's usually inferred indirectly. You measure the star's brightness, crucially its intrinsic brightness, its absolute magnitude, and its color. Then you compare those properties to theoretical models.
Models of how stars evolve.
Right. These models are called isochrones. Think of them as theoretical snapshots on a color magnitude diagram, like an HR diagram. They show where stars of a certain age and composition should lie on that diagram, depending on their initial mass.
So if you know how bright a star truly is, what color it is, and maybe its age and metal content.
You can find its position on the diagram and read off what initial mass the models say it must have had to get there.
But getting the intrinsic brightness, the absolute magnitude, that requires knowing the distance, doesn't it?
Bingo! You measure the apparent brightness, how bright it looks from Earth. To know how bright it really is, you have to know how far away it is to correct for the one distance squared dimming.
And that is where Gaia comes in, finally.
That is where Gaia comes in, the European Space Agency's mission. Its primary job is astrometry, measuring positions, motions, and crucially distances with unprecedented accuracy.
Using parallax, right? That tiny wobble in a star's apparent position as Earth orbits the sun.
Exactly. The bigger the wobble, the closer the star. Gaia measures these tiny angles for over 1 billion stars, giving us geometric distances that don't rely on assumptions about the star itself.
And that accuracy in distance translates directly into accuracy for absolute magnitude.
Yes, which then translates into much more reliable mass estimates when compared to those theoretical isochrones. Gaia's parallax data is just fundamentally improving our ability to characterize the present-day mass function.
Especially nearby, I guess. In the solar neighborhood and maybe nearby star clusters.
That's where its precision is highest, yes.
Right.
The solar neighborhood is suddenly becoming this incredibly well-characterized benchmark region.
Perfect place to really try and pin down the IMF for stars like those in our part of the galactic disk.
It is. We have Gaia distances, but also lots of other data spectra, velocities. But even with Gaia, getting from the present-day function to the initial function, even locally, is still tricky.
Still have to deal with those corrections.
Yep. You've got a mix of stars here, younger ones in the thin disk, older ones in the thick disk. They have different ages, different metallicities, stars formed at different rates over time. Lots of stars are binaries that Gaia might see as one star.
Right. An unresolved binary looks brighter than a single star of the same type.
Which messes up your magnitude, and therefore your mass estimate if you don't account for it. And then there's dust. Dust between us and the stars makes them look fainter and redder. You have to correct for that, too.
Okay, so Gaia provides the crucial distance anchor, the foundation, but you still need careful modeling to peel back the layers of evolution, dynamics, binaries, and dust.
Exactly. It's not magic, but it's the essential ingredient we were missing for so long.
So what have people actually found using this powerful new tool? Let's talk specifics from studies using Gaia's data release 2, DR2.
Okay, yeah. Several key studies came out using DR2 that really started to sharpen the picture. One was by Salima in 2019. They focused purely on the solar neighborhood within about 300 parsecs or so.
A decent chunk of space around us.
Yeah, using about 120,000 stars from Gaia BR2. And they really tried hard to account for all those complications we just listed, unresolved binaries, metallicity spread, the star formation history.
And what did their IMF look like? What shape did they find?
They found it was best described by a segmented power law, but with 2 breaks in the slope. They saw a peak, or maybe a flattening, around 0.15 solar masses. Below that, it didn't rise as steeply.
Okay, a turnover at the low mass end. What about above that?
Between about 0.15 and 1 solar mass, the slope they found was around modic of 1.34. which actually was pretty consistent with what many previous studies had found for that range.
So kind of confirming the standard picture for low to solar mass stars.
In that specific range, yes. But the surprise came at the higher masses, above 1 solar mass.
What happened there?
Their slope was much steeper than most previous studies had suggested. They found values between about negative 2.68 and negative 2.41, depending a bit on their assumptions.
Wait, steeper. Steeper than saltpeter's original negative 2.35 even.
Yeah, significantly steeper than many widely used IMF parameterizations.
So if their result holds up, it means there might be considerably fewer massive stars being born in our neighborhood than we often assumed.
That's the implication of their analysis of the DR2 data in that volume, yes. Fewer high-mass stars relative to intermediate mass stars.
And did they weigh in on the universality question?
They did. They compared their derived solar neighborhood IMF to IMFs inferred in other places, like young clusters or external galaxies using other methods and data. And their conclusion was that the differences suggested the IMF is probably not strictly universal.
Interesting. Even if they didn't see a clear trend within those other environments they looked at, just comparing our neighborhood seemed different enough.
Right. So one piece of Gaia-based evidence pointing towards non-universality.
Okay, what else? Were there other studies digging into potential variations within the local population?
Absolutely. A really influential study came out in 2021 from Halakun and Maus. They also looked nearby, within 250 parsecs, but they took a different tack. They used Gaia kinematics, the star's velocities and orbits, plus colors and magnitudes to separate stars into different populations.
So trying to isolate, say, the thin disk stars from the thick disk stars or halo stars that might be passing through.
Precisely. They looked at the dominant thin disk that's most stars near the sun, younger, on nice circular orbits in the galactic plane. For them, they found an IMF that looked, again, pretty standard.
Broken power law, similar slopes to Krupa or Chabrier.
Yeah, a slope of about negative 2.03 above half a solar mass and negative 1.34 below that. Very much in the ballpark of previous estimates.
Okay, so the normal population looks normal. What about the others?
This is where it got really fascinating. They looked at the thick disk stars, older, puffier orbits, and also halo stars that were relatively metal-rich. These groups showed a similar low-mass slope to the thin disk, but their high-mass slope was a bit steeper, around negative 2.35.
Okay, a subtle difference for the older, kinematically hotter populations.
But then they isolated the low metallicity halo stars. These stand out on color magnitude diagrams, sometimes called the blue sequence halo stars.
And what did their IMF look like?
Completely different. It was distinctly bottom-heavy.
Bottom-heavy, meaning way more low-mass stars relative to high-mass ones compared to the disk.
Exactly. They found it was best described by a single, much shallower power law with a slope of just -1.82, holding over most of the mass range they could measure.
Wow, that's a really significant difference. Why is that population like that?
Well, this is huge. Firstly, that kind of bottom-heavy IMF is reminiscent of what some studies suggest exists in the centers of massive elliptical galaxies, very old, different environments. But secondly, these specific low metallicity halo stars.
Yeah.
Many astronomers believe they are debris from a dwarf galaxy that the Milky Way cannibalized billions of years ago, something called the Gaia Enceladus or Gaia sausage merger event.
You're kidding. So these stars might not even be native Milky Way stars.
Many of them likely aren't. They were formed in a completely different galaxy with probably different conditions, maybe 10 billion years ago, and then got shredded and mixed into our halo.
So finding they have a different IMF isn't just a variation within the Milky Way. It could be a fossil record of a different star formation mode from a different time and place.
That's exactly the implication. It's powerful evidence that the way stars form, the resulting IMF, can be different depending on the galactic environment and perhaps the epoch.
Mind blown. Okay, any other recent results adding pieces to this puzzle?
Yes, one more to mention. From Lee and colleagues in 2023, they took a slightly different approach again, using detailed spectroscopy for about 93,000 M-dwarfs, those are low-mass stars, out to 300 parsecs. Spectroscopy gives you good estimates of metallicity and can help with age dating.
So focusing just on the low mass end, but with extra chemical and age information.
Right. And they found clear evidence that the IMF for these M-dwarfs is variable, and it depends on both metallicity and age in a combined way.
Oh, not just one or the other. How did it depend on them?
They found that the oldest stars seem to have fewer low-mass M-dwarfs relative to slightly more massive stars, regardless of their metallicity. But among the younger stars, the proportion of low-mass stars actually increased with increasing metallicity.
Huh. That's complex. So age matters. And for younger stars, metallicity matters in the opposite way you might naively expect if metals just helped make smaller stars.
It seems more nuanced than any simple single trend. It really highlights that you probably need to consider the interplay of these different factors, age, chemistry, maybe kinematics, to understand the IMF variations fully.
So pulling these threads together, Salima finding a steeper high mass slope locally, Halakun and Maus finding distinct IMFs for thin disk, thick disk, and especially that accreted halo component, and Lai et al. Finding age and metallicity dependencies for M dwarfs. What's the big picture emerging from Gaia DR2?
The big picture is pretty clear now, I think. The idea of a single, perfectly universal IMF is really looking untenable, at least in detail.
Even within our own galaxy, let alone comparing to others.
Exactly. These high-precision studies in the solar neighborhood are showing robust evidence for variations linked to kinematics, metallicity, age, and galactic origin. The IMF seems to be modulated by the properties and history of the stellar population itself.
So, the debate that raged for decades, Gaia seems to be providing the crucial evidence to say, yes, there are variations.
It really is. It's giving us the resolution, literally and figuratively, to see these differences that were maybe hinted at before but were hard to confirm. We're moving beyond just arguing if it varies to trying to understand how and why it varies.
And this is still relatively early days for Gaia data, right? There's more to come.
Oh, absolutely. We're currently working with DR3, and future data releases are expected to bring even better parallax and proper motion accuracy, especially for brighter stars that were tricky earlier. Plus, more stars will have better metallicity estimates, better information on dust extinction, better identification of binary stars.
So the picture will only get sharper.
That's the expectation. Each release should allow us to probe these variations with even greater confidence and detail, really mapping out the IMF across different populations and hopefully connecting those variations back to the underlying physics of star formation.
Wow. Okay, what a journey. We started with the IMF just as this concept, this birth census for stars.
Yeah, this empirical description. Then we touched on the theories trying to explain it, fragmentation, feedback.
And that huge, long-running debate about universality. Is it the same everywhere or not?
Followed by the real practical headaches of actually measuring it, correcting for stellar evolution, for dynamics, the difficulty of getting masses, the crucial need for distance.
And then boom,
Yeah.
Gaia, providing those critical distances with amazing precision.
And enabling these studies we discussed, looking closely at our local neighborhood and finding that it's complicated. The IMF does seem to vary between different populations right here in the Milky Way.
Depending on their age, their motion, their chemistry, even maybe if they came from another galaxy originally.
Exactly. The simple picture of universality is giving way to a more nuanced understanding.
So let's leave our listeners with a final thought to chew on. If the way stars form, this fundamental distribution of masses they end up with, if that can actually differ depending on the conditions.
Like the age of the universe when they formed, the metal content of the gas, the dynamics of the environment, maybe even the history of galactic mergers.
What does that imply about the sheer variety of stellar populations out there? And maybe, just maybe, the variety of planetary systems they host. Could different environments preferentially make different kinds of stars, leading to different kinds of planets or maybe different likelihoods for life across the cosmos, or even just across the different parts of our own Milky Way?
That's a fascinating implication to consider, isn't it? How the birth conditions echo through the types of stars and potentially the worlds that orbit them.